Chapter 13, Thermodynamic Property Relations. Okay, class, today we are going to talk about something very special in thermodynamics called property relations. And I promise to make it simple, like a story you can tell a friend. Imagine you have a magic notebook where you write down everything about your favorite toy: its size, color, weight, and how fast it goes. Thermodynamic property relations are like this notebook, but for gases and liquids. Some properties are easy to see and measure, like temperature and pressure, just like how you can see your toy's color. But others, like internal energy, enthalpy, and entropy, are hidden, just like the excitement you feel when playing with the toy. You can't see it directly, but it's there. So scientists created smart ways to figure out these hidden properties using the things we can measure. We start with something called partial derivatives. Think of it like focusing on one thing while ignoring everything else. Like if you want to see how your toy's speed changes when you push it harder, but you ignore the wind or the road. In thermodynamics, we use this method to see how one property changes while keeping others steady, and we call it partial derivative. Next comes Maxwell relations, which are like shortcuts. Instead of doing hard calculations, these are tricks that allow us to figure out hidden properties just by measuring things like pressure, volume, and temperature. It's like knowing the weight of your toy without using a weighing scale, just by measuring its size and the material it's made from. Then we have the Clapeyron equation, which is a smart way to calculate how much heat is needed when something changes phase, like ice melting or water turning into steam. You only need to measure how pressure and temperature change, and voila, you can find out how much energy is involved. We also learn about specific heats, which are like how much food your toy needs to get active. Some materials need more energy to heat up, just like some toys need more batteries to run. Specific heat at constant volume, CV, is like heating something in a closed box where it can't expand, while specific heat at constant pressure, CP, is like heating it with a loose lid where it can expand. Then we discover the Joule-Thomson coefficient, which tells us if a gas gets cooler or hotter when it flows through a small hole without exchanging heat, like air coming out of a balloon. Some gases cool down, others heat up. It depends on their natural behavior. Finally, we learn cool tricks like the Mayer relation, which shows the relationship between CP and CV. There's also something called entropy, which tells us how messy or orderly energy is inside our system. Using these property relations, we don't need to measure everything directly. We can be like detectives, using clues from simple measurements to know everything about our energy system. In the end, property relations are like a magic guidebook for engineers, helping us understand the hidden world inside steam, air, and refrigerants just by using a few simple measurements. That's it for today. Next time we will play with these formulas and see how engineers use them to build better engines, coolers, and power plants.